All right, let's have a look at the homework that's due Monday. So what we have here are three shear and moment diagram problems. All right, so the first one there is we want to draw up shear moment diagrams for this beam here. All right, so what you're going to want to do is to first find the reactions. So you're going to take moments about A. You take the 9,000 Newton force times the 4-meter moment arm. That's negative because it's clockwise. Then the 24,000 Newton meter couple, which is negative also. No moment arm on that because it's just a couple. It already has the moment arm in it, okay? So you don't need to put another one in there. It's already there. And then plus 12 times the reaction at D. That'll get you RD at 5,000. And then you could some moments about D or some forces in the Y, whatever. I took moments about D just to get a check on my work. So I had minus 12 times whatever RA is, because that would be clockwise for this upward reaction. And then 9,000 times 8 meters this time, positive for counterclockwise. Then minus 24,000 for the couple. And that got me RA on the left at 4,000. And then I notice if I add the two together, I'll get the downward force. Okay, so that all checks out. All right, so now you have the reactions. So you have all the forces acting on the beam. So you go ahead and draw up the shear diagram. So what you're going to do is start at 0 on the left, kick up by 4,000, which is the reaction. Then there's nothing going on until you hit the 9,000 Newton force. So that takes you from 4,000 down to 5,000. So you're dropping by 9,000 from 4,000 to negative 5,000. And then you'll hold. Notice that couple has no direct force, no direct effect on the shear diagram. It affects the reactions, which affect the shear diagram, but it doesn't affect the actual drawing of the diagram. So you'll just go over to point D at negative 5,000, then the reaction pushes you back up. All right, once you have that, you want the areas under the shear diagram. So 4,000 by 4 gets you 16,000 right there. 5,000 times 4, it's a negative 5,000 because you're below the x-axis there is negative 20,000. That gets you up to here where that couple is. And then you can find the area on the other side, which is also negative 20,000. Okay. So I want to get the area on either side of that couple because I know the couple will cause an extreme change in the shear diagram. All right, the next thing here is I'm going to have the moment diagram. That'll start at 0 and we'll have a change equal to the area under the shear diagram, which in this case is 4,000. So it starts at 0, goes with a constant slope. Whoops, I'm sorry, the area is not 4,000, it's 16,000. There we go. So we go from 0 up to 16,000. The slope of that line is equal to the value of shear, which is positive 4,000. All right, the next run here is going downward because we've got a negative area of 20,000. Okay, so we're going from 16,000, we're dropping by 20,000 to negative 4,000. Again, that's at a constant slope equal to the value of the shear, negative 5,000. Okay, then you have the couple. The couple is 24,000 negative, but you change the sign when you look at how a couple affects the moment diagram. So we'll get an immediate change in moment of 24,000, but it's positive on the moment diagram. So the beam reacts in a positive sense to that negative 24,000 that's applied. So you end up from negative 4,000, you now jump up to 20,000. So negative 4,000 plus the 24,000 gets you 20,000. Then that last area to the right of the couple is negative 20,000, so that brings you back down to 0. Okay, again, that'll be at a constant slope. The slope is equal to the value of shear, negative 5,000. Okay. So there's the first one. Okay, the second one here, we've got a cantilever beam. So what we want to do with this is I found the total area under the load diagram, negative 4,000 times 6 meters, okay? It's negative 24,000 and it's centered at 3 meters over. So basically for the sake of finding reactions, we can take that distributed load and turn it into a 24,000 point load at 3 meters off. Now we only use that to find the reactions, okay? So sum of fx is 0, obviously, that's rax. Sum of fy will be ray up minus the distributed load, the 24,000 down, minus the 8,000 point load. I'm converting everything into newtons here. Down, so ray is 32,000. Then I can find the reactive moment that you would have at the wall. It's MRA, which is what I want to find, minus the 24,000 times the 3 meter offset. It's clockwise, so that's a negative. That's coming around like that. Likewise, the 8,000 times 4 is clockwise, so it's negative. So I can solve for MRA, it's 104,000. Okay. So once I've got that, I can go ahead and get the shear diagram. So what I do here is I'm going to find the area on either side of this 8,000 kilonewton, excuse me, 8,000 newton, which is 8 kilonewton load. So here I've got negative 4,000 there because it's down. So negative 4,000 times the distance of 4 is negative 16,000. On the other side, I got negative 4,000 times 2, which is negative 8,000. Okay. So I start here at 0. I go up by the couple. Now the couple is, I'm sorry, not the couple, the reaction. We're on the shear diagram here, my bad on that. So by the reaction there, so I go up immediately up to 32,000. Then I'll drop by 16,000. And that'll get me down to 16,000 right here. Okay, so that's the area under the load diagram from A to B. Then I've got the 8,000 newton load down, so that'll drop me from 16,000 down to 8,000. Then I've got the last bit of area here is negative 8,000, which gets me from 8,000 down to 0. I've got constant slopes on these lines equal to the value of the load diagram, which is negative 4,000. And then, so that's the slope of these two lines. And I have that little discontinuity here where this point load pushes the shear diagram down by 8,000. All right, now once I've got that, I want to get the areas under the shear diagram. So I got 32,000 and 16,000. I've got a trapezoid there. So 32,000 plus 16,000 over 2 times the base of 4 gets me the area. It's 96,000. And then I've got 8,000. Then I got a triangle here with a height of 8,000 and a base of 2. So that has an area of 8,000. Okay. So now I can get to the moment diagram. I start at 0. I've got that reaction of 104,000. That's positive. It's counterclockwise. Okay. So that's a positive moment on account of the fact it's counterclockwise. So what I'm going to do with that is I will start at 0 and then immediately go down the opposite sign of the applied moment. So when you have an applied moment, you got to remember to turn the sign around. Okay, so I'm going to turn the sign around and I'm going to go down by that amount. So that concentrated moment there gets me an immediate change in the moment diagram of negative 104,000. Okay, so then I come up by 96,000, which is this first area. So negative 104,000 plus 96,000 gets me to negative 8,000 right there. And then in the next run there, I'll come up by 8,000 more, and that'll close me off at 0, where I should be. Okay, so I go from negative 104,000 up to negative 8,000, then from negative 8,000 to 0 on account of these areas under the shear diagram, which are the changes in the moment diagram. All right, I've got a positive slope here and a less positive slope at point B. So that slope becomes less positive, so it's concave down. Similarly, I've got a positive slope at B to the right of B and a slope of 0 at C, I think at the end of the beam. So that gets me that concave down shape also. Okay, the last one was the handout that I gave you. It looks something like this. It's in Moodle. It's homework problem 345. So we've got this beam here. First thing to do is to find the reactions, as you do. So I want to find the total area under the load diagram. Negative 600, because those are downward arrows for the load, times 12 feet is negative 7,200 pounds. Now that would be centered at 6 feet. When I find the reactions, that location for that distributed load is at the centroid of the rectangle, halfway across at 6 feet. So when I sum moments about A, I got a clockwise 7,200 by 6, that's negative. 4,000 by 4, which is this load right here. And then I've got the couple of 26,400, which is also negative. Reacting to that is 12 times RC, so RC is 8,800. Then I can go sum of Fy, I got RAY up minus the 7,200 for the distributed load, minus 4,000 for the point load, plus the reaction of 8,800, so I get RA is 2,400. So those are my reactions. All right, so I'm going to start at A at 0. I'm going to go up by 2,400. Then I'm going to start to come down by an amount that equals the area under the load diagram. Now I've got this big point load at 9 feet over, so I want to find the area to the left of it on the load diagram. So negative 600 times 9 is negative 5,400. I'm at 2,400 and I drop by 5,400, so I end up at negative 3,000. So I'm going 2,400 minus the area of 5,400, and that gets me to that negative 3,000. Okay, then I go down by another 4,000 on account of that point load, so that gets me down to negative 7,000. Then I drop by the rest of this area. Negative 1,800 is negative 8,800. So that's where I end up there. So negative 7,000 minus that next area of 1,800, that gets me at negative 8,800. Then the reaction there, which is a point load, pushes it back up to 0. Okay, so I end up back at 0. So there's the shear diagram. Now once I have that, what I want to do is calculate the area under the parts of the shear diagram. So what's going on here is I want to find this 0 point here, okay, because that's a change between positive and negative area on the shear diagram. So I'm at 2,400 there on account of that reaction there on the left. I'm dropping by a slope equal to the value of the load. That's 600 pounds per foot. So if I divide that out, I get 4 feet. That's where that zeroes out. So I got 4 feet on this side. I had a total of 6, 3 and 3, so I got 2 feet on the other side. Okay, so that gets me a couple triangles that I can find the area of. So 1/2 times 2,400 times 4, which is the base, gets me 4,800. And then on the other side, I got 1/2 times negative 1,200, because that's where I end up there. When I work my way over to the shear at 6, it's negative 1,200. So 1/2 times that, times negative 1,200 times its base of 2 gets me an area of negative 1,200. Okay, then I've got some other shapes in here to handle too. I've gone this far so far. Now I cut it there because I've got this couple at B. I know that's going to change my moment diagram and give me a discontinuity, so I want to find the area to the left. So now I'll find the area to the right. I've got a trapezoid. The heights are negative 1,200 and negative 3,000, so I find the average height minus 1,200 minus 3,000 over 2. The base there is 3 more. Okay, so 3. The 3 is that number right there. That's negative 6,300 for that first trapezoidal area. For the second, I've got a height of 7,000. For the left, on the right, I got a height of negative 8,800. Divide that by 2, multiply it by the base of 3. And what I get there is I get an area of negative 23,700. Okay, so I got 4 of those areas worked out, working my way across, so I can make the moment diagram now. Okay. So what happens first is I start at 0, as I would for any sort of diagram. I then go up by the amount equal to the area of this triangle. So at 4 feet, I'm at a height of 4,800. Then I have a change in moment equal to the area under the shear diagram from there up till point B, and that's negative 1,200, so that gets me down to 3,600. So 4,800 minus 1,200 is 3,600. Then I hit this couple at 26,400. That's clockwise, so it's negative, so it causes the moment diagram, which reacts to that, to be positive. So I got 3,600 and then I add that 26,400 to it, and I end up at 30,000. Okay, so that's the height up there. Then I've got this next area, which is negative 6,300. Okay, I'm at 30,000. I drop by that amount. So I take away that next area, and that next area then is 6,300. So I take that away, and I end up at 23,700. So that's the value of moment right there. And then this final area takes me back down to 0. Okay. So that's the moment diagram there. Now, the other thing on this is the shape. Okay, you just look at the slopes. The slopes equal the value of the shear diagram. So I start off at a slope of positive 2,400. Up here I'm at 0, and up here I'm at negative 1,200. So that gets me concave down. Then I have that discontinuity brought in by the concentrated moment. Then I've got a slope up there, which equals the value of shear, which would be negative 1,200. Then a more negative slope here at negative 3,000. A little bit of a discontinuity there where the slope changes to negative 7,000. Then finally a slope of negative 8,800. So again, that's concave down. So that's a run through the homework. I do have a solution posted for this one if you want to look at it. It's there.